Dear friends, today we're going to talk about negative skin friction concept. What is negative skin friction? Negative skin friction is a downward force. Please follow my cursor. Downward force exerted on a pile by a surrounding soil. In some cases, the downward drag force may be excessive and cause foundation failure. Such a force can exist under the following conditions. 1. Clay fill is placed over a rectangular soil layer, as shown in this figure. A clay fill, this is artificial fill, not natural strata. So the consolidation process will exert consolidation because this clay fill will undergo a consolidation and downward volume decrease. And this downward volume decrease will exert a downward drag force on the pile. Actually, this is a rare case. The common case is second case. Granular soil fill, as shown in this below figure, granular soil fill is placed over a layer of soft clay. This is a very common case because on soft soil, generally we apply a granular fill for soil reinforcement, soil improvement, or increase level, surface level. In this case, consolidation in the clay layer. Due to what? Due to excessive load of granular fill. Consolidation in this clay layer exert downward drag on this pile again. Third case may be lowering of the groundwater table. Groundwater table decrease may increase the vertical stress on the soil, and so this will induce consolidation settlement in clay. If a pile is located in the clay layer, it will be subjected to a downward drag force again. This is again rather rare case, but general case is the second case. Let us talk about group piles. Up to now, we have discussed capacity of one single pile. But in fact, we apply pile foundation in group. And a pile cap is constructed for these group piles. When the piles are placed close to each other, as shown in this figure, and suppose that these curves represent stress distribution, and when these two piles are placed close each other, as you see here, stress distribution of these two piles may overlap in this region, resulting in superposition and increased stress. So this may reduce capacity of piles. Ideally, the piles in a group should be spaced so that the load-bearing capacity of the group is not less than the sum of the bearing capacity of the individual piles. A good design should satisfy this condition. The sum of total capacity will be equal to group capacity. In practice, the minimum center-to-center pile spacing, I mean between center to center, this should be 2.5 D, 2.5 diameter, pile diameter. And in ordinary situations, it's actually about 3 or more. The efficiency of the load-bearing capacity of a group pile can be defined as shown in this equation. Nu here represents group efficiency, and QU, QGU is ultimate load-bearing capacity of the group pile, ultimate capacity of group pile, and here QU, ultimate bearing capacity of each pile without the group effect. Sigma means cumulative all the piles, capacity of all the piles. Nu can be estimated using this method, Converse-Labarre equation, Converse-Labarre method, and the equation is given here. M1 and N2 are number of piles in row and column, in other words, X and Y and X direction. For example, in this example, N1 is 3 and N2 is 3 again. What else you see here in this equation? Theta. Theta is degree and equals to inverse of tangent of d over d, capital D over d. Diameter divided by spacing. If the center-to-center spacing d is large enough, so this parameter nu will be greater than 1. In that case, the piles will behave as individual piles. Thus, in practice, when this parameter n and nu is less than 1, then we will multiply this n with summation of piles in group to get ultimate load-bearing capacity of the group pile. But if nu is equal and greater than 1, we don't need to apply any correction. Let us discuss further ultimate capacity of group piles in saturated clay case. Please follow this figure. In this figure, 1, 2, 3, 4, 5 by 3 piles are placed in group and combined with pile cap. And this pile cap will distribute total capacity, total load into these piles. Referring to this figure, We can estimate the ultimate load-bearing capacity of group piles in the following manner. I will explain step by step. In step 1, we will determine sigma QU. Sigma QU will be equal to capacity of one single pile, actually summation of QP and QS, end bearing and shaft bearing, and then we will multiply with number of piles in the group. Because we know how to determine QP and QS in saturated clays, actually we use in this equation, which is shown in brackets. And in step 2, we will determine the ultimate capacity by assuming that the piles in the group act as a block with dimensions LG, BG, and L. Suppose that our pile group with soil inside behave as a huge raft foundation, as a huge mud foundation. So we will consider shear strength at the side of this block, not inside, at the side of this block, and bearing again under this block with soil inside. So in step 2, the skin resistance of the block will be equal to side area, actually LG plus BG times 2. What does it mean? Perimeter multiplied by delta L. This will be equal to side area, and multiplied by Cu means side frictional resistance. When we have more than one layer, so we have to use shear strength of every layer, and cumulative of this equation will give you total side capacity or skin resistance of this block. How can we calculate end bearing? End bearing, very simple. Area multiplied by QP, because we determine QP as Cu times NC, and area equals to L times B, L of group multiplied by B of group. Then this is the point bearing or end bearing capacity. You know, NC is obtained from figure 948. This is modified bearing capacity factor, N star. So final capacity can be written as in this equation. By the way, this method is also called Terzaghi-Peck block analysis. This method is called Terzaghi-Peck block analysis. Yes, this is NC factors. In step 3, we will compare the values obtained in step 1 and step 2. So the lower of two values is taken as group ultimate capacity. Comparison between step 1 and step 2 will give you the group capacity. Let us solve an example question. This is not from textbook, it's from a different source. A group of 9 piles, as shown in this figure, 3 piles in row, was driven into soft clay, extending from ground levels. The diameter and the length of the piles are given 0.3 and 10 meters respectively. The unconfined compressive strength is given 70 kilopascal. If the piles were placed as shown in this figure, the center to center spacing is 90 centimeters. Compute the allowable load on the pile group on the basis of a shear failure criterion and for the safety factor 2.5. The allowable load on the group is to be calculated for 2 conditions: block failure and individual pile failure, as shown in these 2 steps, step 1 and step 2. And the minimum one will be taken as group capacity. We need area and perimeter and such geometrical properties of this block. And actually we need Cu, but as you notice, unconfined compressive strength is given. As you remember from soil mechanics course, for saturated clays, Cu equals to half of unconfined compressive strength. So Cu can be taken as 35 kilopascal. Let us start with block analysis. In block analysis, 35 Cu and multiplied with area 4.4 and perimeter multiplied by Cu and length, the total capacity is 4,326. What about single piles approach? In single pile approach, we'll determine capacity of a single pile, multiply with number of piles, 3 by 3. And this is equal to 3,166. So as you see, this is less than block analysis. So we can take this single pile approach as group ultimate capacity. Dividing with safety factor, we will get allowable bearing capacity of group. We have one more example. Find the allowable bearing capacity of a single pile in a group of piles as given in this figure, 3 by 4. A. Converse bar formula. B. Terzaki-Peck block analysis. Diameter is 40 centimeters. Undrained shear strength is given as 50. And soil is uniform. We have one single soil layer. Unit weights and safety factors are given again. Center to center distance spacing is 1.2 meters. And that's all. In Converse-Labarre formula, we have M1 and M2. What is we have to calculate? Theta first. As you remember, theta is d over capital D over D, and inverse tangent of d over d equal to 18.4. Just putting this 18.4 here and number of piles M1 and M2. So theta is 0.71 and single multiplied with summation of total piles, it will be equal to 195.8 kilonewton. Of course, before Converse-Labarre equation, we have to determine one single pile equation, one single pile capacity. This is shown here. This 275 comes from allowable bearing capacity of piles. In Terzaghi-Peck group reduction method, first of all, we have to determine perimeter and area, and we need modified NC factor. This comes from figure 948, and it's 8.6. Just putting into the equation, ultimate capacity for single piles is 1081. Dividing by safety factor is 432.5. And as you see, it's greater than the first approach. So minimum one is Converse-Labarre group action method, group reduction method. So we will use this value as allowable capacity of pile group. Up to now, these methods give you allowable bearing capacity. But of course, we have to consider settlement of pile group. The consolidation settlement of a pile group in clay can be estimated by using 2/1 stress distribution method. In other words, we call this method approximate methods. Let me explain step by step again. In step 1, let the depth of embedment of the piles L. Please note that L starts from the below the pile cap. The group is subjected to a total load G sub G if the pile cap is below the original ground surface. This Q sub G equals the total load of the superstructure on the piles minus the effective weight of soil above the group piles removed by excavation. For example, this height will be considered and effective weights will be subtracted. This is step 1. In step 2, assume that the load Q group is transmitted to the soil beginning at a depth of 2.3 L. This is length of pile, and this depth is 2.3 of pile length, AB line. And QG is transmitted to the soil from this under this AB line. The load Q sub G spreads out along two vertical lines, A prime and B prime. Having two vertical, one horizontal slope. In step 3, we will calculate the increase in effective stress caused at the middle of each layer. For example, in this layer, we will calculate stress increase for this depth, mid layer. Similarly, for this clay layer, we will determine stress increase at midpoint of this layer. You have to know from soil mechanics, the stress increase at the mid layer is calculated using this equation, Q divided by B plus Z. What is that? Depth at mid layer. Again, L plus Z. After calculating stress increase, delta sigma, in step 4, we will calculate the consolidation settlement of each layer caused by the stress increase for each layer. And the same equation can be practically rewritten by these equations. You are more familiar because you know from soil mechanics course. In soil mechanics course, we use these equations. Actually, these two equations are the same, just rewritten or reorganized. And the summation of all settlement values for each clay layer is equal to settlement of group, consolidation settlement of group. S represents settlement, sub C is used for consolidation settlement, and this G represent group. Group settlement of group, consolidation settlement of pile group. Let us solve one example question about pile settlement problem. A group pile, as shown in this figure, and we will determine consolidation settlement of pile group. We have 1, 2, 3. 3 clay layers, and all clay layers are normally consolidated, so we can use this equation, normal consolidated clay equation. Parameters are given for every layer. Unit weight initial void ratio, and C sub C, consolidation index. What else we need? Block dimensions. Block dimensions are given, file group dimensions, 3.3 meter and 2.2 meter. Length of files is 15 meters, so stress distribution starts from this depth 2 over 3 of pile length. Total load applied to group is 2000 kilo. Let us start to calculate. We will use this equation for normally consolidated clays. So we need C sub C and E0 there, and compressible layer thickness. All are given in this table, and we need effective stress and stress increase for mid layer of every clay layers, and we'll used here. Let us start to calculate layer by layer. Delta sigma 1 and effective stress for the first layer, I mean this point, are calculated as 51.6 kilopascal and 134.8 kilopascal respectively. So we know soil parameters. Just putting these two here. Consolidation settlement for the first layer is 162.4 millimeters. Let us do same thing for second clay layer. Again, we need effective stress and stress increase for the mid layer of the second clay. Please note that how to calculate this, how to determine these ZI values. Or let us do layer by layer. For the first clay layer, the thickness is 7 meters, so half of the thickness is 3.5. We have 10 meters above this line, but actually in clay we have 9 meters and 1 meter sand anyway, and the Z value will be taken as 3.5. Then for the second layer, the thickness is 4 meters and midpoint is 2 meters. Starting from this location, 7 plus 2, that will be 9 meters. 9. Let us do the same thing for the third clay layer. And 2 meters, half of 2 meters, 1. So 7, 11 plus 1, 12. and Z is 12 meters. This may be confusing. Please do not confuse. What does we need? Applying the same procedure for the third layer, effective stress, stress increase, and consolidation settlement. So we have three consolidation settlement values. Of course, cumulative of these three will be equal to consolidation settlement of group. This is 183.5 millimeter. Do you have any question up to now? No question? Okay. Let us go into details somehow, and let us talk about spatial cases in group analysis. This type of group analysis is simple or basic analysis, and we have to consider some conditions, some spatial cases, as shown in these three figures. The soil in figure A, this figure, is homogeneous. Soil is homogeneous. The load Q is assumed to act on 2/3L. This is basic case, which we solved in this example. But in example B, or in this figure B, the soil condition is somehow different. We have strong layer here. The piles pass through a very weak layer down to L1, this zone, and lower portion here, L2, is embedded in a strong layer. In this case, the load Q is assumed to act at a depth of 2/3 of L2. You understand? We will not take L as the whole length of the pile. We have to consider this depth and this thickness, L2. So our fixtures line will pass 2/3 L2 here, and we will distribute stress below this line. In figure C, here the piles are end-bearing piles sitting on a firm stratum. The load in this case is assumed to act at the level of the firm stratum and spreads out at 2/1 slope, but under the firm stratum. These two are spatial cases. Actually, we have analyzed the first case. This is basic case. Let us have one more example. In this example, we have 3 by 4 pile groups, and we will calculate the consolidation settlement of this group, and length of piles 10 meters. Diameter of piles are given 80 centimeters, and spacings are shown, and it's 2 meters center to center spacing. Total load applied on pile cap is 5,000 kilonewton. In soil profile, we have soft clay, and under the soft clay, we have a dense sand, incompressible, dense sand. Under this dense sand, we have again clay. Under the clay, the layer is rock. The soil condition is different. So let us first consider this soil profile, and let us decide which condition is applicable to our profile. The soil is not homogeneous, and this basic model cannot be used. Actually, we have firm stratum. The second and third cases may be applied. Let's consider. In the second case, piles are embedded to strong layer, firm layer. Let us check. In our case, piles are not embedded. So the model, which is shown in figure C, is applicable to our site condition. And let us solve. So what does it mean? Our stress distribution will start at the end of these piles. In this figure, the stress distribution lines are shown and starts from end of the pile. We can use MV method because as compressibility parameter, MV is given, coefficient of volume compressibility, MV is given, so we can use this equation. For this equation, we have MV, but we need compressible layer thickness. Compressible layer thickness is shown here, 6 meters, and the midpoint is located at 3 meters above rock. So H is taken as 6 meters. We have to calculate delta sigma. We can use this depth as shown in dashed line, and we can solve in one calculation. But generally, for thick clay layers, it's preferred to divide clay layer into sublayers. Let us do this method in this example. Let us divide this clay layer into 2 and calculate for every layer. So in this case, Our compressible layer thickness will be 3 meters for each sublayer, imaginary layer, and delta sigma values will be calculated for the mid depth of every layer. Then delta sigma 1 and delta sigma 2, these are two stress increases. Stress increases can be calculated as total load divided by enlarged area here. In other words, block dimension plus depth. What is block dimension? It's shown here, 6.8 and 4.8. We will add depth of this layer. We have 3 meter here and 1.5 meter, total 4.5. So 6.8 plus 4.5, 4.8 plus 4.5. Then delta sigma 1 is 47.6 kilopascal. Let us apply the same thing for this second sublayer, second imaginary sublayer, delta sigma 2. Here, total load will be divided into area of this layer, this is mid layer, and block dimensions will be increased with depth of this point. What is depth of this point? 3, 6 plus 1.5, 7.5. Increasing by 7.5, and delta sigma 2 is 28.4. Let us put into this equation MV is given, thickness of every layer are equal, and this 2 equals to 3. Taking into delta sigma parenthesis, delta S is equal to 2.28 centimeters. Any question up to now? Is there any question? No? Okay. New chapter is lateral earth pressure and design of retaining structures. As you remember from soil mechanics course, lateral earth pressure can be simply analyzed by Rankines methods or Rankines theory. Of course, we have other analysis methods, but Rankines method is well accepted and worldwide common methods. So in designing retaining structures, we will use Rankines methods, Rankines basic methods. And first of all, I want to repeat Rankines theory. You know from soil mechanics, but it's just for reminder. And after this summary, we will go into retaining wall design. But not today. Next week Next week, we will start to lateral earth pressure and design of retaining structures. Today I am closing the lecture. See you next week. Of course, if you don't have any question. If you have, you can ask now.
See you, hocam. Thank you for today.